October 20th, 1943. Somewhere over the North Sea, 30,000 feet above the cold grey water, Captain Robert Johnson of the 56th Fighter Group eased his P-47 Thunderbolt into formation, scanning the sky for the telltale contrails of German fighters. Below and ahead, a formation of B-17 flying fortresses droned toward their target deep inside Germany, their aluminum skin glinting in the thin sunlight. Johnson's fuel gauge was already showing concern. They were approaching the limit of the Thunderbolt's range, and the bombers still had hundreds of miles to go before reaching their target. Within minutes, Johnson and his fellow escorts would have to turn back, leaving the bombers to face German fighters alone over the most heavily defended airspace in Europe. This scene repeated itself daily throughout 1943. American bomber crews watched their fighter escorts peel away at the German border, then faced wave after wave of Luftwaffe interceptors without protection. Loss rates climbed to unsustainable levels. Some missions saw 20, 30, even 40 bombers fail to return. The arithmetic was brutal and undeniable. At this rate, the entire 8th Air Force would be destroyed before Germany's industrial capacity could be meaningfully degraded. What the Americans desperately needed was a fighter that could escort bombers all the way to Berlin and back, a fighter that could dominate German interceptors at the altitudes where combat occurred, a fighter that combined range, speed, and high-altitude performance in a single airframe. That fighter already existed, sitting on airfields in England, but in October 1943, almost nobody realized it yet. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The North American P-51 Mustang had entered service with the Royal Air Force in 1942 as a low-altitude tactical reconnaissance and ground attack aircraft. American pilots who flew it praised its handling characteristics and long range, but dismissed its combat potential due to inadequate high-altitude performance. The aircraft's Allison V-1710 engine, reliable and powerful at low altitudes, gasped for air above 15,000 feet, where German fighters operated most effectively. At 25,000 feet, a Mustang powered by the Allison engine could barely exceed 390 miles per hour, making it slower than the German Messerschmitt Bf 109 and Focke-Wulf 190 at combat altitudes. The aircraft was fast enough for ground attack missions, but completely unsuitable for high-altitude bomber escort duty, where speed and climb performance were essential for survival. But buried in that seemingly inadequate airframe was extraordinary potential waiting to be unlocked. The Mustang's aerodynamic design was fundamentally superior to any fighter aircraft flying in 1943. Its laminar flow wing, developed using advanced wind tunnel testing, produced less drag than conventional wing designs. Its carefully streamlined fuselage minimized parasitic drag. Its radiator installation, positioned behind and below the cockpit with carefully designed ducting, actually produced slight forward thrust from the cooling air rather than pure drag. These features combined to create an airframe more aerodynamically efficient than anything the Germans had achieved. What the Mustang needed was an engine that could exploit this efficiency at high altitude. What it needed was the Rolls-Royce Merlin. The Merlin engine represented the culmination of British aero engine development stretching back to the 1930s. Rolls-Royce engineers had created a liquid-cooled V12 engine that combined sophisticated supercharging with meticulous attention to internal airflow, combustion efficiency, and thermal management. The Merlin had powered the Spitfire and Hurricane fighters during the Battle of Britain in 1940, providing just enough performance advantage to counter the Luftwaffe's numerical superiority. By 1943, the Merlin had evolved through dozens of variants, each optimized for specific altitude ranges and applications. The Merlin 61 series, featuring a two-stage two-speed supercharger, could maintain substantial power output at altitudes exceeding 30,000 feet, where earlier engines struggled. The marriage of the Merlin engine to the Mustang airframe was not a sudden inspiration, but rather the convergence of several parallel development efforts driven by British operational needs and American industrial capacity. In April 1942, a Rolls-Royce test pilot named Ronald Harker visited an RAF squadron operating Mustang Mark Is powered by Allison engines. Harker flew the aircraft and immediately recognized that its exceptional low-altitude performance and remarkable handling characteristics were being limited by the Allison engine's inadequate high-altitude capability. He filed a report suggesting that installing a Merlin engine would transform the Mustang into an exceptional high-altitude fighter. Rolls-Royce engineers began preliminary design work on the conversion almost immediately. The technical challenges were substantial, but not insurmountable. The Merlin was physically larger and heavier than the Allison, requiring modifications to the Mustang's engine mounts, cooling system, and cowling. The Merlin rotated in the opposite direction from the Allison, which would affect the aircraft's handling characteristics during takeoff and landing. The two-stage supercharger required additional ducting and intercooler installations. The engine's different fuel and oil systems demanded redesigned plumbing throughout the forward fuselage. Every modification had to be carefully engineered to preserve the Mustang's aerodynamic efficiency while accommodating the new engine's requirements. By October 1942, Rolls-Royce had completed the first conversion of a Mustang airframe to Merlin power. The aircraft, designated Mustang Mark X, flew its initial test flight on October 13, 1942, from the Rolls-Royce facility at Hucknall. Test pilot Ronnie Shepherd reported that the aircraft's performance exceeded all expectations. Maximum speed at 25,000 feet had increased from 390 miles per hour with the Allison engine to 432 miles per hour with the Merlin. Rate of climb had improved dramatically. The aircraft remained controllable and responsive at altitudes where the Allison-powered version became sluggish and difficult to manage. Simultaneously, North American Aviation in the United States had been exploring similar modifications, working with the Packard Motor Company, which was producing Merlins under license for American use. The Packard Merlin, designated V1650 in American nomenclature, was mechanically identical to the British Rolls-Royce version, but used American standards for threads, tolerances, and electrical systems to facilitate mass production in American factories. North American engineers completed their own Merlin-powered Mustang conversion in November 1942, and flight testing confirmed the same dramatic performance improvements that the British had discovered. The technical details of why the Merlin transformed the Mustang's capabilities require understanding the fundamental principles of high-altitude engine performance. Aircraft engines, whether piston or jet, require oxygen to burn fuel and produce power. As altitude increases, atmospheric pressure decreases, meaning each cubic foot of air contains fewer oxygen molecules. An engine that produces 1,500 horsepower at sea level might produce only 750 horsepower at 25,000 feet, simply because the air is so thin that the engine cannot draw sufficient oxygen into its cylinders to maintain combustion efficiency. Superchargers addressed this problem by compressing incoming air before it entered the engine cylinders, effectively restoring sea-level air density even at high altitude. The Allison V1710 used a single-stage mechanical supercharger, driven directly by the engine crankshaft. This system worked adequately at moderate altitudes, but became increasingly inefficient above 15,000 feet. The supercharger consumed substantial engine power to operate, and the compressed air became very hot, reducing its density and limiting the performance gains. The Merlin 61 series used a two-stage, two-speed supercharger system that revolutionized high-altitude performance. The first stage compressed incoming air to an intermediate pressure. An intercooler then cooled this compressed air, increasing its density. The second stage compressed the air further, to the pressure needed for high-altitude operation. A two-speed gear system allowed the supercharger to operate at different speeds depending on altitude, optimizing efficiency across the entire operating range. This complex system consumed more power to operate than a single-stage supercharger, but the performance gains at altitude were so substantial that the trade-off proved worthwhile. The Packard Merlin V1653, the engine variant installed in early production P-51 Mustangs, produced approximately 1,490 horsepower at 3,000 revolutions per minute with 61 inches of manifold pressure. This was roughly comparable to Allison's sea-level output, but at 25,000 feet, where the Allison produced perhaps 800 horsepower, the Merlin maintained over 1,200 horsepower. At 30,000 feet, the performance gap widened further. The Merlin could sustain substantial power at altitudes where the Allison barely functioned. This power advantage translated directly into speed. The P-51B, powered by the Packard Merlin, could achieve 440 miles per hour at 25,000 feet, approximately 50 miles per hour faster than the Allison-powered version at the same altitude. Maximum speed exceeded 440 miles per hour at optimal altitude. More importantly, the Merlin-powered Mustang could reach these speeds while carrying significant fuel loads, including external drop tanks, without severe performance penalties. The combination of the Merlin's high-altitude power and the Mustang's aerodynamic efficiency created a fighter with unprecedented operational radius. With two 75-gallon drop tanks supplementing its internal fuel capacity of 184 gallons, the P-51B could escort bombers on missions covering over 1,300 miles, more than sufficient to reach Berlin from English bases, and return with reserve fuel for combat. No other Allied fighter in late 1943 could approach this combination of range and high-altitude performance. Production of Merlin-powered Mustangs began in earnest during 1943 at North American Aviation's plant in Inglewood, California. The company had been producing P-51A Mustangs with Allison engines, so transitioning to the Merlin-powered P-51B required substantial changes to the production line. Engine mounts had to be redesigned and manufactured to new specifications. The cooling system was completely revised, with larger radiators and modified ducting to handle the Merlin's greater heat output. The aircraft's nose was lengthened slightly to accommodate the Merlin's larger dimensions and to maintain proper center of gravity with the heavier engine. The propeller was changed to a four-blade unit, better suited to the Merlin's power characteristics and opposite rotation direction. These modifications delayed initial production, but by August 1943, P-51Bs were rolling off the assembly line at increasing rates. North American also established a second production line at their Dallas, Texas facility, where the aircraft was designated P-51C despite being virtually identical to the California-built P-51B. The two plants combined would eventually produce over 3,700 P-51B and P-51C models before transitioning to the improved P-51D variant in early 1944. The first P-51B Mustangs arrived in England in October 1943, assigned to the 354th Fighter Group based at Boxted. Ground crews and pilots underwent hasty conversion training, learning the Mustang's systems and flight characteristics. Many pilots were transitioning from P-47 Thunderbolts, and the differences between the two aircraft were substantial. The Thunderbolt was massive, heavy, and powered by a huge radial engine. The Mustang was sleek, relatively light, and powered by an inline engine that required more careful management. The Thunderbolt could absorb tremendous battle damage. The Mustang's liquid cooling system was vulnerable to even single bullet hits that could cause coolant loss and engine failure. Pilots quickly learned that the Mustang rewarded smooth, precise flying technique. Its controls were lighter and more responsive than the Thunderbolts, particularly at high speed. The aircraft accelerated rapidly and maintained energy well through maneuvers, but it required attention to engine management. The Merlin's liquid cooling system had to be monitored carefully to prevent overheating. The two-stage supercharger had to be operated correctly, engaging the second stage at the proper altitude to maximize performance without overboosting the engine. The Mustang's armament on the P-51B and P-51C models consisted of 4 Browning M2 50-caliber machine guns, with 2 guns mounted in each wing. This was lighter firepower than the Thunderbolt's 8 50-caliber guns or the Messerschmitt Bf-109's cannon and machine gun combination. American pilots initially expressed concern about the reduced ammunition capacity and fewer guns. Each gun carried approximately 350 rounds, providing roughly 20 seconds of continuous firing time. But combat experience would demonstrate that 4 50-caliber guns properly harmonized and fired by a skilled pilot, provided adequate firepower for most combat situations. The first operational mission flown by P-51 Mustangs occurred on December 1, 1943, when aircraft from the 354th Fighter Group escorted bombers attacking targets in France. The mission proceeded without incident, serving primarily to familiarize pilots and ground crews with operational procedures. But within weeks, Mustangs would be penetrating deep into German airspace, and Luftwaffe pilots would begin encountering an American fighter unlike anything they had faced before. German intelligence services had been tracking American fighter development throughout 1943, collecting information from combat reports, technical analysis of crashed aircraft, and intelligence sources. They knew the Americans were operating P-47 Thunderbolts, P-38 Lightnings, and various models of the P-51 Mustang. The Allison-powered Mustangs had been assessed as adequate low-altitude fighters, but no particular threat at the altitudes where most combat occurred. When Merlin-powered Mustangs began appearing over Germany in December 1943, Luftwaffe intelligence initially failed to recognize that this represented a fundamentally different aircraft, despite its external similarity to earlier Mustang variants. The first combat reports describing encounters with the new Mustangs filtered back to Luftwaffe headquarters through standard intelligence channels. Pilots reported American fighters with unusual performance characteristics at high altitude. These aircraft could match or exceed the speed of German fighters at 25,000 feet and above. They demonstrated excellent acceleration and sustained high-speed performance. Most troubling, they appeared over German targets hundreds of miles from the nearest Allied bases, indicating operational radius far exceeding any previous American fighter. Luftwaffe intelligence officers initially dismissed these reports as exaggerations born of combat stress. German pilots, they reasoned, were facing overwhelming odds and might be overestimating enemy capabilities. The Americans had shown no previous ability to escort bombers deep into Germany, so reports of American fighters over Berlin or other distant targets must be mistakes or misidentifications. This assessment would prove catastrophically wrong, but the truth would only become apparent through accumulated evidence over many weeks. The strategic situation facing Germany in late 1943 was already grave, despite propaganda claims of inevitable victory. The Eastern Front had stabilized after the failed offensive at Kursk, but Soviet forces were gradually pushing westward with increasing momentum. The Mediterranean theater had been lost with Allied forces firmly established in Italy. Most critically for German war production, American and British bombers were conducting increasingly effective strategic bombing campaigns against German industrial targets. The combined bomber offensive, as Allied planners designated their strategic bombing campaign, aimed to destroy Germany's ability to manufacture war materials through systematic attacks on factories, transportation networks, oil production facilities, and other critical infrastructure. American heavy bombers, primarily B-17 Flying Fortresses and B-24 Liberators, conducted daylight precision bombing raids intended to destroy specific targets with minimal collateral damage. British bombers conducted nighttime area bombing raids that were less precise but created widespread disruption to German war production and civilian morale. The American daylight bombing campaign had achieved mixed results through mid-1943. When German fighters could be avoided or suppressed, American bombers demonstrated remarkable accuracy and destructive capability. But when German fighters attacked in force, American bomber formations suffered devastating losses despite their heavy defensive armament. The famous raid on Schweinfurt's ball-bearing factories on October 14, 1943, illustrated the problem starkly. Of the 291 B-17 seconds that set out for Schweinfurt, 60 were shot down, and another 17 were damaged beyond repair. A 26% loss rate was absolutely unsustainable regardless of the damage inflicted on the target. American strategic planners understood that long-range fighter escort was essential for the bombing campaign's success. Without fighter protection, bomber loss rates would eventually force suspension of daylight operations. The P-47 Thunderbolts, while excellent fighters at high altitude, lacked the range to escort bombers beyond Western Germany. The P-38 Lightnings had adequate range, but suffered mechanical problems in the cold European climate and lacked the high-altitude performance needed to consistently dominate German interceptors. What the 8th Air Force needed was a fighter combining long-range, high-altitude performance and reliability. The Merlin-powered Mustang provided exactly that combination. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical specifications of the P-51 Mustang revealed why it succeeded where other designs had failed. The aircraft's empty weight was approximately 6,940 pounds. With full internal fuel and ammunition, combat weight reached approximately 9,000 pounds. With 2 external drop tanks fully loaded, maximum takeoff weight approached 11,800 pounds. For comparison, the Messerschmitt Bf 109G, Germany's primary fighter in late 1943, weighed approximately 5,190 pounds empty and 7,496 pounds at maximum loaded weight. The Focke-Wulf 190A weighed approximately 7,650 pounds empty and 10,800 pounds maximum. The Mustang was thus intermediate in weight between Germany's 2 primary fighters, heavier than the Messerschmitt but lighter than the fully loaded Focke-Wulf. But the Mustang's power-to-weight ratio at high altitude exceeded both German designs due to the Merlin engine's superior high-altitude performance. At 25,000 feet, a P-51 powered by the 1,490 horsepower, Merlin could out-accelerate and out-climb both German fighters despite comparable or slightly greater weight. The Mustang's wing design deserves particular attention, as it represented genuine aerodynamic innovation rather than incremental improvement of existing designs. North American Aviation's chief engineer, Edgar Schmude, and chief aerodynamicist, Edward Hawkey, had developed a laminar flow airfoil that minimized drag by maintaining smooth airflow over a greater percentage of the wing's surface. Traditional wing designs experienced transition from smooth laminar flow to turbulent flow relatively early across the wing's chord, creating substantial drag. The Mustang's wing maintained laminar flow further back, significantly reducing drag at high speeds. This advantage was most pronounced at speeds above 350 miles per hour, where drag increases rapidly with velocity. The Mustang could sustain higher speeds than aircraft with similar power, but conventional wing designs simply because its wing created less aerodynamic resistance. German engineers who later examined captured Mustangs recognized the sophistication of this design but lacked the wind tunnel facilities and aerodynamic expertise to replicate it in German production aircraft. The cooling system installation represented another area where American engineers had achieved genuine innovation. Most inline engine fighters mounted radiators in the wings or in a large chin scoop under the engine, creating substantial drag. The Mustang's radiator was positioned behind and below the cockpit, with carefully designed ducting that created what aerodynamicists call the Meredith effect. Air entering the radiator scoop was heated as it passed over the hot radiator core. This heating caused the air to expand and accelerate as it exited through the carefully shaped exit duct. Under optimal conditions, the forward thrust produced by this accelerated air nearly offset the drag created by the radiator installation itself. While the Meredith effect never produced net forward thrust, as some enthusiasts claimed, it did reduce cooling drag to levels far below what conventional installations achieved. These aerodynamic refinements, combined with the Merlin's power to create a fighter with exceptional high-altitude performance, maximum level speed of 440 miles per hour at optimal altitude, made the P-51 faster than any production German fighter at typical combat altitudes. The Messerschmitt Bf 109G achieved approximately 400 miles per hour maximum at altitude. The Focke-Wulf 190A reached approximately 408 miles per hour. Neither German fighter could catch a Mustang in level flight at 25,000 feet or above if the American pilot chose to run. Rate of climb comparisons favored the German fighters at low to medium altitudes, but evened out at high altitude where the Merlin's superior power output compensated for the Mustang's slightly greater weight. The P-51 could climb to 20,000 feet in approximately 7 minutes. The Messerschmitt and Focke-Wulf could reach the same altitude, perhaps 30 seconds faster under optimal conditions. But as altitude increased above 25,000 feet, the Merlin-powered Mustang maintained better climb performance, while German engines lost power rapidly in the thin air. Service ceiling represented another significant advantage. The P-51B could operate effectively at 41,900 feet, higher than German pilots normally flew, and higher than German fighters could effectively intercept. American bomber formations increasingly operated at altitudes between 25,000 and 30,000 feet to minimize flak exposure, while remaining above the optimal performance envelope of German fighters. Mustang escorts could position themselves several thousand feet above the bombers, holding the altitude advantage that fighter pilots call energy, the combination of altitude and speed that determines tactical options in air combat. The fuel system design directly enabled the Mustang's extraordinary range. Internal fuel capacity of 184 gallons was supplemented by two external drop tanks, typically carrying 75 gallons each, but sometimes increased to 108 gallons for maximum range missions. Total fuel capacity thus reached 334 to 400 gallons, depending on drop tank size. The Merlin engine consumed approximately 75 gallons per hour at normal cruise settings, allowing flight times exceeding 4 hours with reserves. Combat missions to Berlin required approximately 7 hours total flying time. The Mustang could make this journey with fuel remaining for combat and emergency reserves. No other Allied single-engine fighter could match this combination of combat radius and high-altitude performance. The P-47 Thunderbolt, with maximum external fuel, could barely reach Berlin, and only by operating at optimal cruise settings with minimal combat maneuvering. The P-38 Lightning had adequate range, but its performance at altitude was inferior to both the Mustang and German fighters. The drop tank system worked through carefully designed fuel plumbing that allowed pilots to draw fuel from external tanks first, preserving internal fuel for combat and the return flight. When external tanks were empty or when combat began, pilots released the tanks using cockpit control. The tanks fell away cleanly without damaging the aircraft or creating control problems. Thousands of these disposable fuel tanks littered the European countryside, each representing the extended reach of American air power into what had been German-controlled airspace. December 1943 through March 1944 represented the crucial period when Merlin-powered Mustangs transitioned from experimental novelty to strategic weapon. Initial missions kept the Mustangs relatively close to England, while pilots gained experience with the new aircraft. Gradually, mission planners extended the range, sending Mustang groups deeper into Germany. By early March, Mustangs were regularly flying all the way to Berlin and back, a feat that seemed impossible just months earlier. The psychological impact on both German defenders and American bomber crews was profound and immediate. German pilots, who had learned to time their attacks for the moment when American fighters turned back due to fuel limitations, suddenly found themselves facing fresh American fighters over targets deep inside Germany. The sanctuary that German pilots had enjoyed in their homeland's airspace evaporated rapidly. Luftwaffe tactics had to change from waiting for the escorts to leave to engaging immediately despite unfavorable odds. American bomber crews watched Mustangs escort them all the way to the target and back to England. Loss rates began declining almost immediately. Missions that had cost 20 or 30 bombers in late 1943 increasingly returned, with single-digit losses by spring 1944. The strategic bombing campaign, which had teetered on the edge of failure, suddenly became sustainable and increasingly effective as more bombers reached their targets and returned to fly again. March 6, 1944. The mission planners at 8th Air Force Headquarters designated the target as Berlin, the heart of Nazi Germany, a city that American heavy bombers had never reached in force during daylight hours. The distance from English bases to Berlin measured approximately 600 miles, requiring a round trip of 1,200 miles, plus whatever maneuvering occurred during combat. Colonel Donald Blakesley, commanding officer of the 4th Fighter Group, briefed his pilots with characteristic directness. They would fly to Berlin. They would protect the bombers. They would engage any German fighters that attempted to attack the formations. His operations officer pointed out that this mission exceeded the P-51B's calculated range, even with maximum external fuel tanks. Blakesley's response entered fighter pilot legend. "We're going to Berlin," he stated flatly. The discussion was over. 68 P-51B Mustangs launched from bases across eastern England in the pre-dawn darkness of March 6th. They formed up over the English coast, climbed to altitude, and set course for Germany. Behind them came waves of B-17 and B-24 bombers, 730 aircraft carrying thousands of tons of bombs toward targets in the German capital. German radar stations detected the incoming formations while they were still over the North Sea. Luftwaffe fighter controllers scrambled interceptor units across northern Germany, vectoring them toward predicted interception points. The controllers expected American fighter escorts to turn back at their usual range limits, somewhere near the German border. But the American fighters did not turn back. At each checkpoint where German controllers expected the escorts to withdraw, the Mustangs remained with the bombers. As the formations penetrated deeper into Germany, passing Hanover, approaching Berlin, the controllers' confusion turned to alarm. These American fighters were flying farther than any previous escort missions, maintaining formation discipline despite flying at extreme range from their bases. The first major engagements occurred as the bomber formations approached Berlin from the west. German fighters, primarily Messerschmitt Bf 109 and Focke-Wulf 190 models, climbed to intercept the bombers. They found Mustangs waiting at altitude, positioned with the sun behind them, holding the crucial energy advantage that came from altitude and speed. Lieutenant Robert Goebel of the 31st Fighter Group, flying his P-51B at 28,000 feet over Berlin, spotted a formation of Messerschmitts below, attempting to position for an attack on the bombers. Goebel rolled inverted and dove, accelerating rapidly through 450 miles per hour. He closed on the trailing Messerschmitt, achieved firing position, and fired a short burst from his .450 caliber guns. The Messerschmitt's canopy shattered. The German fighter rolled slowly left and entered a steep dive, trailing smoke and glycol coolant from the shattered engine cooling system. This engagement pattern repeated across the sky over Berlin. German fighters attempting to reach the bombers faced Mustangs diving from altitude with tremendous speed advantage. The bomber formations reached their targets, dropped their bombs through intense flak, and turned westward for the long flight home. The Mustangs remained with them, fending off repeated German attacks throughout the withdrawal. Colonel Blakesley's 4th Fighter Group returned to Debden with every aircraft accounted for. The fuel gauges showed nearly empty tanks, but every pilot had sufficient fuel remaining to land safely. American fighters had escorted bombers all the way to Berlin and back, engaging German fighters throughout the mission. The strategic implications were immediately apparent. Germany's airspace was no longer a sanctuary. American bombers could now reach any target in Germany with fighter escort. German intelligence officers compiled the combat reports from March 6th with growing alarm. Their pilots reported American fighters over Berlin in force that had not turned back at the usual range limits. Most troubling, these American fighters demonstrated performance characteristics that exceeded previous American types at the exact altitudes where German doctrine emphasized fighting. Luftwaffe technical intelligence identified the aircraft as P-51 Mustangs, but the performance reports did not match their existing data on earlier Allison-powered variants. German intelligence requested additional information from frontline units. The answer came from examination of crashed Mustangs recovered from combat zones. German technical teams discovered that these Mustangs used Rolls-Royce Merlin engines, built under license by Packard, rather than the Allison engines found in earlier models. More complete understanding came in April 1944, when Luftwaffe forces captured an intact P-51B after the pilot, disoriented during combat, mistakenly landed at a German-controlled airfield. The aircraft was immediately transported to Rechlin, the Luftwaffe's primary test facility, for detailed evaluation. Hans-Werner Lerche, the Luftwaffe test pilot who had evaluated numerous captured Allied aircraft, flew the Mustang and filed detailed reports that confirmed what combat pilots had been reporting. At altitudes above 25,000 feet, the Merlin-powered Mustang was faster than any production German fighter. Maximum speed at 25,000 feet exceeded 440 miles per hour, approximately 40 miles per hour faster than the Focke-Wulf 190A. Range with drop tanks exceeded 1,300 miles, sufficient for missions to Berlin and back with combat reserves. The reports also identified weaknesses that might be exploited tactically. The Mustang's Merlin engine used liquid cooling, making it vulnerable to coolant system damage. The armament of 450 caliber machine guns was lighter than the mixed armament typical of German fighters. These tactical advantages were real, but increasingly irrelevant, as the strategic situation deteriorated. The expansion of Mustang operations through spring and summer 1944 demonstrated American industrial capacity operating at scales Germany could not match. By June 1944, 8 fighter groups in the 8th Air Force flew P-51 Mustangs. North American Aviation's production facilities were producing P-51 Mustangs at rates exceeding 400 aircraft monthly. These production numbers reflected the entire industrial infrastructure supporting fighter production, with Packard producing hundreds of Merlin engines monthly and subcontractors manufacturing thousands of components. The P-51D model, which began reaching operational units in summer 1944, incorporated numerous improvements based on combat feedback. The bubble canopy replaced the P-51B's framed canopy and provided vastly improved visibility. The armament was increased to 650 caliber machine guns. The K-14 computing gun sight automatically adjusted aiming point based on target range and angle, significantly improving hit probability. These continuous improvements reflected an industrial system capable of systematically refining weapons based on operational experience. German industry, by contrast, was increasingly focused on simply maintaining production levels, despite strategic bombing, raw material shortages, and the progressive degradation of manufacturing standards. The strategic air campaign over Europe reached its decisive phase in spring and summer 1944. American bombers, now escorted all the way to their targets by Mustangs, struck German aircraft factories with increasing accuracy. The psychological impact on Luftwaffe pilots became increasingly severe as losses mounted without corresponding replacements. New German pilots arrived at operational units with minimal training, sometimes having logged fewer than 100 flying hours before entering combat, facing American pilots who typically had 300 or more hours of training. Major George Preddy of the 352nd Fighter Group exemplified the lethality of properly employed Mustang tactics. Flying P-51D, nicknamed Cripes A Prime Mighty Third, Preddy accumulated victories through disciplined execution of boom and zoom tactics that exploited the Mustang's high-altitude speed. Advantage. On August 6, 1944, during a single mission, Preddy shot down 6 German fighters. Preddy's tactics were methodical. He positioned at high altitude, waited for German fighters to climb toward bomber formations, then dove at high speed to attack. After each firing pass, he extended away using his speed advantage to disengage. When sufficient separation was achieved, he climbed back to altitude and repeated the process. This disciplined approach maximized the Mustang's strengths while minimizing exposure to German countermeasures. The destruction of the Luftwaffe fighter force occurred through systematic attrition. Every major raid cost Germany fighter aircraft and experienced pilots that could not be adequately replaced. By late summer 1944, German fighter units were operating at fractions of their authorized strength. Pilot quality deteriorated as training programs were compressed, and fuel shortages limited training flight time. German attempts to counter the Mustang threat through technological innovation came too late. The Messerschmitt Me-262 jet fighter represented a genuine technological breakthrough, approximately 100 miles per hour faster than any Allied piston engine fighter. But production never exceeded modest numbers due to manufacturing difficulties, engine reliability problems, and Allied bombing of production facilities. German fuel shortages became critically acute by autumn 1944, following successful Allied bombing of synthetic fuel plants. The Luftwaffe instituted strict fuel rationing that limited training flights and sometimes prevented operational missions even when aircraft and pilots were available. Mustang pilots conducting ground attack missions in late 1944 frequently discovered dozens of German aircraft parked at airfields, often camouflaged but immobile and vulnerable to strafing attacks. The operational radius that the Merlin engine had given the Mustang enabled ground attack missions that proved almost as valuable as bomber escort. Lieutenant Colonel Elwin Righetti of the 55th Fighter Group led a fighter sweep on April 7, 1945, that destroyed 23 German aircraft on the ground at various airfields in southern Germany. The Merlin engine's reliability proved crucial to these extended-range missions. Fighter pilots operating hundreds of miles from friendly territory required absolute confidence in their aircraft's mechanical integrity. The Packard-built Merlin achieved reliability rates that exceeded 90%. This reliability reflected American manufacturing quality control and the systematic application of automotive mass production techniques to aircraft engine manufacturing. Packard's production facilities in Detroit employed manufacturing processes that ensured consistent quality across thousands of engines. Each engine underwent rigorous testing before installation. Critical components were inspected using X-ray analysis to detect internal flaws. Assembly workers followed detailed procedures that specified torque values for every bolt and clearances for every bearing. The contrast with German engine production became increasingly stark. Allied bombing disrupted German manufacturing, forcing production to be dispersed among numerous smaller facilities where quality control was difficult to maintain. Raw material shortages forced substitution of inferior materials. German engines in late 1944 showed declining reliability, contributing to the Luftwaffe's operational difficulties. By spring 1945, the Luftwaffe had effectively ceased to exist as a coherent fighting force, despite thousands of aircraft remaining on paper strength. Operational ready rates had collapsed. Fuel allocations were insufficient for even minimal training. The few missions that were flown increasingly ended in disaster as poorly trained German pilots faced veteran American pilots flying superior aircraft in overwhelming numbers. General Lieutenant Adolf Galland, one of Germany's most successful fighter pilots and later commander of German fighter forces, wrote in his post-war memoirs about the strategic implications of the Mustang's appearance. Galland recognized that an American fighter capable of escorting bombers to any target in Germany represented Germany's strategic defeat in the air war. The specific contribution of the Merlin engine to the Mustang's success deserves emphasis because it represented a genuine technological breakthrough. The Allison-powered P-51 was adequate at low altitude but unsuitable for high-altitude bomber escort. The same airframe powered by the Merlin became arguably the finest all-around fighter aircraft of the Second World War. This transformation occurred because the Merlin's two-stage supercharger maintained power output at altitudes where the Allison's single-stage supercharger became ineffective. The 1,490 horsepower that the Packard Merlin V1653 produced at 25,000 feet exceeded what any German production engine could sustain. The 1,720 horsepower, achieved by later Merlin variants, gave the Mustang performance margins that German fighters could not match. The engineering sophistication of the Merlin reflected decades of British development in high-performance aero engines. Rolls-Royce had been producing racing engines during the 1920s and 30s, learning how to extract maximum power from compact engines. The Merlin incorporated features like sodium-cooled exhaust valves and sophisticated supercharger systems that represented the leading edge of piston engine technology. Packard's successful production of the Merlin under license demonstrated American manufacturing capability at its peak. The Merlin used British engineering standards that differed from American standards. Packard converted the entire engine design to American standards, creating detailed manufacturing drawings for every component. This conversion process required approximately 18 months and thousands of man-hours of engineering work. By 1944, Packard was producing more Merlins monthly than Rolls-Royce. The final accounting of the Merlin Mustang's impact requires examining both direct combat results and broader strategic effects. American P-51 units claimed approximately 4,950 enemy aircraft destroyed in air-to-air combat, with the majority occurring in Europe. Additionally, Mustangs destroyed over 4,000 German aircraft on the ground during strafing attacks. These statistics understate the Mustang's strategic significance. The aircraft's primary mission was protecting bombers, and by this measure, the Mustang succeeded completely. Bomber loss rates declined dramatically after Mustangs became available in quantity. The strategic bombing campaign that had teetered on failure in late 1943 became increasingly effective as more bombers reached their targets safely. The human cost of this air campaign was staggering on all sides. The 8th Air Force alone suffered approximately 26,000 men killed in action. German fighter pilots died in numbers that approached 90% of those who saw extensive combat. These casualties reflected the brutal arithmetic of industrial warfare, where victory belonged to the side capable of sustaining losses while systematically destroying the opponent's capacity to continue fighting. The Merlin engine's transformation of the P-51 Mustang illustrated fundamental principles about modern warfare. Superior technology mattered, but only when combined with industrial capacity to produce it in quantity, logistics systems to deliver it to combat zones, training programs to create skilled operators, and tactical doctrine to employ it effectively. Germany possessed excellent engineers and produced some technically advanced weapons, but lacked the industrial depth to compete with Allied production operating at continental scale. The marriage of British engineering excellence in the Merlin engine with American aerodynamic innovation in the Mustang airframe and American mass production capability created a weapon system that exceeded the sum of its parts. Neither the British nor the Americans could have achieved this result independently. The combination of British technology and American production created the capability that defeated the Luftwaffe. The legacy of the Merlin Mustang extended beyond its wartime service. The aircraft remained in production until 1951, with over 15,000 examples built. The aircraft served in combat during the Korean War. Many Mustangs survive today, carefully restored by collectors who recognize the aircraft's historical significance. The sound of a Merlin engine remains distinctive and immediately recognizable to aviation enthusiasts. The characteristic rumble of the V12 engine at idle, building to a powerful roar at full throttle, evokes memories of an era when piston-engine fighters represented the pinnacle of aviation technology. For Germany, the appearance of Merlin-powered Mustangs over Berlin in early 1944 confirmed what thoughtful observers already understood. Germany was fighting opponents with industrial capacity that exceeded German capacity by overwhelming margins. The Mustang represented not just one excellent aircraft design, but an entire industrial system capable of conceiving, developing, producing, and supporting complex weapons in quantities sufficient to achieve strategic objectives. When German pilots first encountered Mustangs over Berlin in March 1944, they faced not just a superior aircraft, but a complete system of integrated capabilities that Germany could observe and measure, but never replicate. The Merlin engine's 1,720 horsepower at high altitude was less important as an isolated specification than as a symbol of Allied industrial and technological advantages that Germany could not overcome. The air war over Europe ended in May 1945 with complete Allied victory. Among all contributing factors, the Merlin-powered P-51 Mustang stands out as a weapon system that directly enabled Allied strategic objectives, by providing the long-range, high-altitude fighter escort capability that the bombing campaign required to succeed. Without the Mustang, the daylight strategic bombing offensive would likely have failed due to unsustainable losses. With the Mustang, the bombing campaign achieved its objectives and contributed decisively to Germany's defeat. The 1,720 horsepower Merlin engine had turned an adequate fighter into an exceptional fighter, and in doing so, had helped turn the tide of the air war over Europe toward inevitable Allied victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.